Today we're going to talk about base fields that are fixed by automorphisms and how we build functions that do that. So automorphisms are isomorphisms from a field to itself, and we're going to talk about what it means to fix a base field. And that means we're just going to move stuff around that we've adjoined. So let's look at an example we've already talked about. We've got the conjugation automorphism from the complex numbers to themselves, which I'm writing in a slightly weird way. This way that I'm writing it will help me illustrate what I mean by fixing a base field, in this case R. Okay, so what does it mean to have an automorphism? Well, first of all, we need a homomorphism. So when we check that it's a homomorphism, we check that it preserves addition and multiplication. And we've seen for both of these that the conjugate of a sum is the sum of the conjugates, and the product works the same way, so the conjugate of a product is the product of the conjugates. We've also checked that it was injective, or one-to-one, meaning that if we have alpha and beta that give us the same output, the same conjugates, then alpha and beta had to be the same thing. We also checked that it was surjective, so given a target complex number, let's call it alpha, we need to know how to get there. And in this case, if we take alpha and the complex numbers, and our complex numbers here is the copy that's sitting in our codomain, then when we take C of alpha bar, we get alpha bar conjugate, which is just alpha. And it's an automorphism because the domain and codomain here are the same things. So isomorphism is when we have a one-to-one and onto, or a bijective homomorphism. And automorphism is when we have an isomorphism from a space to itself. Okay, so what does it mean to say that it fixes R? Well, that just means that the complex conjugate of every real number is just the real number itself. So that's pretty good. That tells us that our conjugation automorphism is determined by what C does to the complex number I, right? The complex conjugate of I is negative I. And that's because C of A plus BI is going to be C of A plus C of B times C of I. And we're just using the fact that that's a homomorphism of rings. And that's going to be A plus B times C of I, because we said it fixes the real numbers, and A and B are real numbers. And that is A minus BI because C sends I to negative I. And that's the conjugate. That's A plus BI conjugate, as we had hoped.